Today's lesson is our second lesson on 2.4, where we're going to learn to add and subtract numbers written in scientific notation. Now there is a key concept for this lesson that we need to know and that we need to be aware of. And our key concept is that numbers must be written with the same power of 10. So the exponents for our numbers in scientific notation must be the same. And I'll show you what that looks like in just a moment. So let's take a look at a couple examples. For our first couple examples, we're going to look at some problems where we're adding numbers together that are written in scientific notation. So for our first example, we have 8.9 times 10 to the 10th plus 4.8 times 10 to the 10th. So what we're going to do here, we're just going to bring our 10 to the 10th right down. We're not going to do anything to that. Okay? So times 10 to the 10th, that does not change. What we need to do is the key concept again says numbers must be written with the same power of 10. Here we have 10 and 10 for our exponents, so those are the same. So there's nothing that we need to do or nothing that we need to change before we begin adding this problem. Okay? Now we just go ahead and make sure that our decimals are lined up and we add these numbers going straight down. 9 plus 8 gives us 17. Carry the 1. 1 plus 8 plus 4 gives us 13. So we end up with 13.7 times 10 to the 10th. Okay? So again, all I've done here, I made sure that my exponents are equal. That's the key concept. We need to make sure that our exponents are equal. I've done that, and so once I have my exponents equal, I bring down the power, excuse me, and then I just go ahead and add the multipliers or the numbers out front. So our multipliers in this problem are 8.9 and 4.8, and I simply go ahead and add those together. And I end up with 13.7 times 10 to the 10th. Now here's my issue that I'm dealing with now though. This answer is not written in correct scientific notation. Okay? So we need to make sure that we need to alter our answer so that it is written in correct scientific notation. Remember that we need a single digit number in front of the decimal. So what I'm going to do is I'm going to move my decimal to in between the 1 and the 3. That gives me a single digit number in front of the decimal. But what I've done is I've taken my number in front and I've changed it from 13.7 to 1.37. So my number in front has gotten smaller. My number in front has gotten smaller. That means if we think of it like a teeter-totter or a seesaw, my exponent has to become bigger. So I end up with 1.37 times 10 to the 11th power. Alright, so that's our first example. Let's take a look at another example of adding numbers written in scientific notation. For my second example, we have 3.8 times 10 to the 5th plus 6.1 times 10 to the 4th. Now here is a problem where we need to pay close attention to our key concept. The difficulty that we're going to have with this problem is that our exponents are not equal. My exponent in the top number is 5. My exponent in the bottom number is 4. I need to make sure that those numbers are equal before I can proceed. And what I would encourage you to do is this. I would always encourage you to match the bigger exponent. Okay? I could take the top number and change that exponent to a 4. I'd have to change the multiplier or the number out front. I could change it to a 4. But that would likely lead to me having to do more work at the end of the problem. But if I go ahead and change my bottom number to give it a higher exponent, changing my bottom number to 5 instead of to 4, that would probably lead to me getting a correct answer where I don't have to do any work at the end of the problem. So what I'm actually going to do here is I'm going to rewrite the problem over to the right. I'm going to write 3.8 times 10 to the 5th. And I'm adding to that. Instead of writing 6.1 times 10 to the 4th, I need to make this exponent into a 5. So that means this exponent needs to get bigger to become a 5. And if my exponent becomes bigger, then my number out front needs to become smaller. So in order to make this smaller, I need to change that from a 6.1 to 0.61. Okay? My exponent gets bigger, so my number in front gets smaller. So I'm going to rewrite that as 0.61 times 10 to the 5th. I make sure that my decimals stay lined up. So now I have 3.8 times 10 to the fifth plus 0.61 times 10 to the fifth. And I recognize that my bottom number is not written in correct scientific notation. But when we're doing adding and subtracting, that's okay. As long as our final answer ends up in scientific notation, then it really is okay. So we're going to add 3.8 plus 0.61. And so when we do that, we get 1. 8 plus 6 is 14. Carry the 1. And we get 4.41 times 10 to the fifth power. All right, and that is our final answer there. 4.41 times 10 to the fifth. I have a single digit number in front of a decimal, so at that point I am good with that answer. Okay, let's take a look at a couple more. Let's take a look at a couple more where we are subtracting now. Our next example, we have 7.6 times 10 to the third minus 6.8 times 10 to the third. With this example, and with all problems dealing with adding and subtracting, we need to make sure that our exponents are equal to each other. Here, in both numbers, our exponent is 3, so we don't have to do anything to manipulate or to change up the exponents at all. In addition to that, our decimals are already lined up, so what we can do is we can just go ahead and subtract these two numbers. So I'm going to write down my times 10 to the third. And now I'm just going to pay attention to my numbers in front, the multipliers or the numbers out front. 6 minus 8, I can't subtract that, so I'm going to borrow 1 from over here. 16 minus 8 gives me 8. Bring down my decimal. 6 minus 6 gives me 0. So I have 0.8 times 10 to the third. Problem here, though, again, is that we cannot have a 0 as our only number in front of the decimal. We need to move our decimal behind the 8. Okay? So we go from 0.8 to 8. That makes that number bigger. So if that number gets bigger, my exponent needs to get smaller. Okay? So from 0.8 times 10 to the third, our correct answer should be 8 times 10 squared. All right? And that's our final answer for example 4. Let's take a look at one more. For our last example, or for our fourth example, I should say, we have 3.5 times 10 to the 13th minus 6 times 10 to the 12th. First thing that we look for when we're adding or subtracting is we need to make sure that we have equal exponents. Right now we do not. We have 13 for our top number, and we have 12 for our bottom number as our exponents. So I'm going to rewrite these numbers next to it, changing it up so that I have equal exponents. So I want to make my numbers match by my bigger exponent. 13 is bigger, so I'm going to take 3.5 times 10 to the 13th. And now I'm going to subtract from that, but I need to change my bottom number to give it a bigger exponent. So my exponent here has to go up. That means my number in front has to become smaller. So it becomes 0.6 times 10 to the 13th. All right, now my exponents are equal to each other, so I can copy down my times 10 to the 13th, and I take 3.5 minus 0.6, again making sure that my decimals are lined up. I'm going to borrow from this 3. 15 minus 6 is 9. Bring down my decimal. And so I end up with 2.9 times 10 to the 13th power. Okay? And at that point, I am all done with that problem. All right, I want to look at a couple more problems. This time, these two problems are going to deal with the populations of Canada, the U.S., and Mexico. Okay, so the countries in North America. Our first problem that I want to do is I want to actually add the populations together to find the entire population of North America. So we're going to add Canada's population to the U.S. population to Mexico's population. So here's what that's going to look like. So I have 3.38 times 10 to the 7th plus 3.1 times 10 to the 8th plus 1.1 times 10 to the 8th. Now, my population for U.S. and Mexico both have the same exponent, the exponent 8. Canada, however, has an exponent that's too small. So what I need to do is I need to increase the size of my exponent for Canada, but if that exponent gets bigger, that means my number out front must get smaller. Okay? So instead of being 3.38, I'm going to change that to 0.338. So I'm going to rewrite it. Yes, I'm going to rewrite the entire thing, and you are too. I'm going to rewrite it to 0.338 times 10 to the 8th plus 3.1 times 10 to the 8th plus 1.1 times 10 to the 8th. Now I want you guys to notice how I'm keeping my decimal points in a line and I'm keeping my powers in a line as well. Alright, all my exponents, all my powers are the same. So I'm going to write that down, giving me times 10 to the 8th. And now I'm going to go ahead and add my numbers together. Well, 8 plus basically blank spaces, 8 plus nothing is going to give me 8. 3 plus nothing is going to give me 3. Now I add 3 plus 1 to give me 5. Bring down my decimal. 3 plus 1 is going to give me 4. So the population of the entire North American continent is going to be 4.538 times 10 to the 8th power. Alright, so that's my first example dealing with populations of North America, of countries in North America. Let's take a look at one more. For our last example, I want to take a look at comparing Mexico's population to Canada to see how many more people Mexico has in it compared to Canada. So we're going to subtract. It's going to be a subtraction problem if we're trying to find out how many more people Mexico has. So we're going to take 1.1 times 10 to the 8th, and we're going to subtract from that 3.38 times 10 to the 7th. Alright, now again my issue that I was dealing with the last example, my exponents are still not equal. So I need to rewrite this problem using equal exponents. So I again need to increase my exponent to 8, and if my exponent goes up, my number in the front, my multiplier in the front, has to go smaller. So I end up with 1.1 times 10 to the 8th, and I subtract from that 0.338 times 10 to the 8th. Alright, so I'm going to write down my times 10 to the 8th. Now I'm going to have to do some borrowing here. I'm actually going to rewrite my green times 10 to the 8th. It gives me a little bit more room to do my borrowing. So I'm going to borrow from here, giving me 10 here, but I'm going to borrow from that, make that a 9, and this becomes a 10. So 10 minus 8 gives me 2, 9 minus 3 gives me 6, and 10 minus 3 gives me 7. So I end up with 0.762 times 10 to the 8th. Well, my issue here, my number is not written in correct scientific notation again. I need a single digit number in front of the decimal. So I'm going to make this number bigger. Making this number bigger by moving the decimal place after the 7. I go from 0.762 to 7.62. And if that number gets bigger, my exponent here must get smaller. So times 10 to the 7th. Alright, and that's my final answer. 7.62 times 10 to the 7th. That is how many more people there are in Mexico compared to Canada. Alright, make sure that you write down any questions that you might have. We will go over a couple bell work problems on this tomorrow and answer any questions that you have on that as well. Just kidding, there's actually one more thing that we need to talk about. We need to talk about scientific notation on a calculator. This is not worth a whole new lesson, so I just want to go over some quick examples of what scientific notation on a calculator is going to look like. Now on a calculator, it is not going to be able to write times 10 to the whatever power, although some of the more recent ones are doing that now. What they do instead of using times 10 to some power, they use e to some power. Okay? So for example, if you have the number 3.1 times 10 to the 7th, and that number is given to you in answer form on a calculator, it's going to be 3.1 E7. Okay? That's the only thing there is. Okay? So instead of using times 10, they use E. So if you get an answer on your calculator, if you're punching in some numbers in your calculator and you get a very big number, that looks like 7.41 E13, that simply means 7.41 times 10 to the 13th power. Okay? That's all that means. All right? That's it now. That's all we have for our lesson. Any questions, write them down. We'll go over this tomorrow.